Hi, Astronomy. Mr. Janowski here. Look, I have a new toy. I got a new microphone. This is the Audio Technica AT 2005 USB. So hopefully it's going to improve the quality of the audio in my videos. So anyhow, this is part 5 of the chapters 14 and 15 astronomy slides. So we've talked about stars during their lives, when they're on the main sequence and what comes after that. And today we're going to deal with their deaths. And then in the parts after that, we'll start to deal with what their different corpses look like. So let's get started with that. So after its main sequence lifetime, a low mass star goes red giant, yellow giant, red giant, and then what? After that, the next stage of its life is planetary nebula. Well, this is really its death. So what is the corpse of a low mass star? The corpse of a low mass star is a white dwarf. So for stars less than 8 times the mass of the sun, they'll live their life, they'll do their thing for a very long time. And then at the end, they're going to die in a planetary nebula, and the corpse they leave behind is going to be a white dwarf. So after its main sequence lifetime, a high mass star goes yellow giant, red giant. Then what? After that, it's going to go supernova, which is a poor name. Nova meaning new. People thought these were new stars. These are actually high mass stars dying and exploding and becoming very bright. So what is the corpse of a high mass star? Well, it depends. A lower mass high mass star, so a star that's about 8 times the mass of the sun up to about 20 times the mass of the sun, will end up being a neutron star. If it's more than about 20 times the mass of the sun, its corpse will be a black hole. So all of these corpses, white dwarfs, neutron stars, and black holes, we'll get to later. They're all very interesting. They're very bizarre things, and we'll get to talk about them. But today we're going to talk about the deaths of stars, basically. So this is a bad misnomer. Planetary nebula. They have absolutely nothing to do with planets. Nebula means cloud. So Sir William Herschel, our old buddy, he named Planet George. He would look through his telescope and he would see these nebulas, and he could tell that they weren't points like stars are. So he thought they might be planets. A reasonable guess, because through the kind of telescopes he was looking at, he would see little planets and they would look not like points, they'd be a little bit fuzzy. So yeah, these things would look a little bit fuzzy too. So yeah, he called them planetary nebula. And that's really a terrible name for them. They have nothing to do with planets. A planetary nebula is actually the glowing shell of gas around a dying low mass star. So if you can look at this image down here, so gas cloud, protostar, main sequence star, where it spends most of its life, and then red giant, yellow giant, red giant again. And at this point, the outsides are just going to kind of drift away, and you're left with just the glowing gas corpse of the star, basically. And that's what a planetary nebula is. So we used to think that planetary nebula tended to be spherical. So the star would just kind of, the outer layers, once the star gets too big, they just kind of drift away, and they would do so in a spherical fashion. So like this, case A up here. However, now that we have better and better telescopes and we see more and more of these things, it turns out they can get really complicated. So yeah, some of them will just, disperse in a sphere. Others will leave something like this. So we think this may be due to perhaps a binary companion to this star. So if you had this star here when it was alive and another star going around it, in this kind of plane here, well, this star eventually gets to its death and it just releases its layers, and it would have been a sphere, only the binary is still going around the corpse of this star. So maybe the binary is sweeping this stuff out and changing the shape of this, is one possible guess. So yeah, sometimes it will actually look like this. So try to look at this guy and imagine you're looking at something like this, but rotated about 90 degrees towards us. So this weird hourglass shape, now we're looking kind of at the bottom of the hourglass. So maybe this is the bottom and we're looking up through it. This is the core in the middle, and then looking through it, we're seeing the other side of the hourglass. So it's a possibility. The other thing, if it's not a binary companion going around, I've heard maybe they think it could just be the planets that were going around the star continue to go around and affect the way the gas drifts away. So, yeah, the gas is drifting away. It's doing so relatively quickly, but you're not going to see it if you're watching it in real time. But if you take pictures of this nebula years apart, you can see it expanding. So, yeah, it happens, and it happens visually and noticeably visually over periods of years. So after about 10,000 years, which takes, that's basically nothing in astronomy terms, the expanding gas just becomes diffuse and part of the interstellar medium. So when it's still near enough to the hot, dead core, it's still getting energy from that core, and that's causing it to kind of shine like this. But eventually it just drifts far enough apart and gets so undense, diffuse, that, yeah, it's not a planetary nebula anymore. So the star's life cycle is complete. It went from gas cloud, it went to being a protostar to a star, lived its whole life as a star, died, and now a lot of its stuff is a gas cloud again. And what's left behind, the corpse of this star, so the core of the star when it was alive and doing fusion is what we say is a living star. Well, the corpse, the core is still there. It's still very hot. It's just not doing fusion anymore. So that core is the corpse of this star. It's a tiny glowing ball called a white dwarf. And we'll talk about white dwarfs more in upcoming slides, but not in this part. So that's how a low mass star dies. So for high mass stars, if you have 8 times the mass of the sun while you're alive or more, you're not going to end up being a planetary nebula. So this is why the dividing line is where it is. So these guys have a lot more mass. Gravity's crushing down a lot more. So they're going to keep fusing the things into heavier and heavier things, is basically what's happening. And this process is called nucleosynthesis. So this is the formation of heavy elements by fusion processes. So nucleo, think nucleus of an atom, synthesis, they're making it. They're synthesizing the nucleus. They're making the nuclei. So, yeah. And I'll go through this chart a little quickly. If you're watching this on your phone, this text is going to be too small to read. But let's see. So this is how long each of these stages lasts in a 25 solar mass star. So the biggest part of its life will be fusing hydrogen into helium. And the minimum temperature required in the core for that is 5 million degrees Kelvin. And, this 25 solar mass star, so its mass is 25 times the mass of the sun, it'll do that for about 7 million years. And then after that, it's going to start to fuse helium into carbon. This is the triple alpha process. So it takes 3 heliums, so 3 atomic element number 2, and it makes 1 atomic element number 6, carbon. So the minimum temperature for that is 100 million degrees Kelvin. So the first one happens at 5 million Kelvin. This one takes 100 million Kelvin. So it'll do that for a while, and then it'll start to fuse carbon with helium into oxygen. And that requires a higher temperature. That's 200 million Kelvin. And that whole stage, helium into carbon, and then carbon and more helium into oxygen, that'll last about 700,000 years, which sounds like a long time, but it's only a tenth as long as, its main sequence, hydrogen into helium stage. After that, more things start happening. I'll do this part a little quicker. So it's going to take carbon and fuse them together and give us neon and more helium. And it'll do that for about 300 years, which again is long in terms of a human lifetime, but tiny in terms of the life of a star. Then it'll start fusing neon plus neon into magnesium and oxygen. And that it will only do for about 8 months. So now we're dealing with more human types of scales. That's less than a school year long. And then it'll do oxygen plus oxygen into silicon and helium. And it will do for about 3 months. And then the last one, it's going to fuse silicon and silicon into iron. And that stage is only going to last 1 day. So it's neat the way these phases work. The first stage, 7 million years. Next stage, 700,000 years. Then 300 years. Then 8 months. Then 3 months. And then this last stage, fusing silicon plus silicon into iron, only lasts for 1 day. So the formation of an iron core signals the end of a massive star's life. So all the other fusion it's done up to this point required a lot of energy to make happen, but it gave the star more energy out of it than it took to make it happen. Iron is the swing point in this process. So it takes a lot of energy to try to fuse iron into anything else, but you get less energy out of it than you had to put in, which means you're not getting the energy you need to counteract the gravity. So you're trying to fuse iron, but you're losing every time you do it. So the whole time the star was alive, remember we had this hydrostatic equilibrium. So gravity was trying to crush it, and pressure from nuclear fusion was counteracting gravity, and it was supporting it. It was trying to blow it apart. Now we get to this point, we're trying to fuse iron into iron plus iron or iron plus anything else. And every time that happens, you lose energy instead of gaining energy to counteract the gravity. So very, very rapidly, in less than a second, this is going to happen at this point. Once it starts trying to fuse the iron, all of the outer layers are going to come crashing down. Gravity's suddenly going to win. It had nuclear fusion holding it at bay. All of a sudden, the pressure from nuclear fusion disappears, and all the outer layers collapse onto the star. So the electrons of the iron atoms are squeezed into the nucleus. So you remember, basically how a nucleus works. Protons and neutrons in the middle and electrons on the outside. Well, in this instant, those electrons are going to get squeezed down into the nucleus. So we're going to end up taking electrons, jamming them into protons, and so -1 plus +1 gives you 0. We formed neutrons. So this whole thing is going to take less than a second. And so this core, this Earth-sized iron core, so even though the star was a giant star at this stage, the core of the star was only the size of the Earth. And once gravity starts crushing it all down, you're going to end up with something only about 20 kilometers across. So very, very tiny. We'll see images later on. They always compare this to Manhattan for some reason. So yeah, the core goes from being, the star itself is huge. It's many, many times the size of the sun, but its core is only the size of the Earth. And then in less than a second, the whole thing is going to get squeezed down into something the size of a city. So very dramatic changes happening all of a sudden. So yeah, this will detail what happens in a supernova a little bit more. So yeah, we no longer have that extra energy to give us the pressure from nuclear fusion to counteract gravity. So all the layers come crashing down. So they crush it. All of a sudden, everything gets really, really hot because of the ideal gas law, PV equals nRT. So this huge pressure is going to suddenly blow everything apart, and you get this enormous explosion called a supernova. And nova means new, and it's actually a terrible name for this. We call them novas or supernovas because you may look up in the sky and see nothing, and then all of a sudden you see a bright point in the sky. So astronomers were calling those new stars. Well, they're not actually new stars. Those are stars that have just died. So supernovas are crazy, crazy bright. A supernova can briefly shine more brightly than all of the other stars in its galaxy combined. So we may have hundreds of millions of stars in a galaxy, and all of those stars, make a very bright galaxy. And then one of them goes supernova, and that one star is brighter than all of the 100 millions of other stars in its galaxy. So in the book's words, the supernova is a quick and glorious death. So a little bit dark, but it does go out in a blaze of glory. So in just a few minutes, as the supernova is exploding, it's going to release more energy than the star did during its entire lifetime. So this star has lived for 7.7 million years. It's a very high mass star, and that's short for the life of a star. But it released a lot of energy in 7.7 million years. And then in the next several minutes, it's going to release even more energy in the instant of its death. So yeah, quick and glorious. So here's the Crab Nebula. We've looked at this before. So the supernova explosion that formed the Crab Nebula was witnessed on Earth on July 4th. Hey, the 4th of July, but several centuries too early, in 1054. So this thing was so bright, you could see it during the day. So imagine looking up at the sky on a clear blue day, And over in one part of the sky, there's the sun, and then in another part of the sky, you see a star. You're not supposed to be able to see the stars out on a bright, clear blue day, but this thing was so bright, you could see it through the daylight. So it was visible in broad daylight for several weeks afterwards. So it doesn't say so here, but it was still visible at night for about a year, and then eventually it faded away. So supernovas also release a lot of energy in the form of neutrinos. So these are these very bizarre things that don't interact with anything practically ever. They go through 4 light years worth of lead with a 50-50 chance of getting stopped. So these are these very unreactive things. And neutrinos are very unmassive. They're very, very light particles, but there's so many of them, they carry away a lot of energy. So if you were alive in 1987, which I was, I would have been, depending on the time of year, I would have been 10 or 11. More than 1 trillion, so this number of neutrinos, would have passed through me from supernova 1987A in the Large Magellanic Cloud, 163,000 light years away. So the Large Magellanic Cloud is one of the galaxies that's kind of orbiting the Milky Way. You can't see it from the northern hemisphere. It's only a southern hemisphere thing. And one of the stars there, this little fellow right here, went supernova. So here on the left is the before, and here's the after. So, yeah, it was witnessed in 1987. It didn't really happen in 1987. This thing is 163,000 light years away. So it actually happened 163,000 years ago. And the light traveled and the neutrinos traveled to Earth, that whole time. And if you're a little, 11-year-old me standing around, more than 1 trillion neutrinos from this supernova would have shot through me. So, yeah, you're learning a lot about me. So what does this leave behind? It leaves behind a supernova remnant. So this is the huge glowing cloud of stellar debris that expands after a supernova explosion. So this is going to carry the heavy elements that the high mass star created during the last stages of its life and during its death. So remember, a low mass star gets up to carbon, oxygen, and a little bit further than that, but doesn't get all the way up to iron. And then that one drifts apart in a planetary nebula, and that releases, those lower atomic number elements out into the universe. So these supernova remnants are going to do kind of the same thing, only when they were alive, they made the heavier things. And I don't think I say so in the slides right here. So remember, the supernova got up to iron, and trying to fuse iron into other things is what killed it and what made it explode. In this instant, when you have this thing exploding so violently, it does get up to temperatures high enough that it can create the things past iron. Iron is only number 26 on the periodic table, and the periodic table goes way higher than that. It's this instant of the supernova when it's making all of the heavier things. It's making the gold, it's making the silver, the selenium, the uranium, the plutonium. All of these things, these really high mass things, are getting created during this instant of this high mass star's death. So, yeah, I think the book is right. This is quick and glorious. So, yeah, this thing explodes in a supernova, shoots all of this stuff out, and then it becomes a gas cloud. Now, this gas cloud, like it says right here, is going to start with more heavy elements than the previous one, because, the first star didn't have many heavy elements, did its whole thing, started to make the heavy elements, blew up, made even more, and all of that material goes into the next generation of stars. So, to review, who named Planetary Nebula and did so poorly? It was Herschel. Yeah, Herschel looked through his telescope, saw these little smudgy things, saw they definitely weren't points. They're little kind of smudges, which sort of looks like a planet, so I'm going to call them Planetary Nebula. Well, that was a bad name. So these things don't really have anything to do with the formation of planets at the beginning of a star's life. This is a low-mass star dying. So what remains at the center of a planetary nebula? Well, the corpse of the low-mass star is the White Dwarf. So, certainly you can see it in this one. All of the outer layers are just drifting away, and they're being illuminated by this still very hot corpse of the star. So this is the White Dwarf. So that's what's going on here. And then eventually, the outer layers drift far enough away that it's not really related to the corpse anymore, and they just become part of a gas cloud, and the corpse remains. So a white dwarf is the corpse of a low-mass star. So, what do we call the formation of heavy elements by fusion processes? We call this nucleosynthesis. So, yeah, all of this is happening in the core of the star. And remember, main sequence, we're forming hydrogen into helium. And then after that, we start going into the giant phases. So, red giant and yellow giant. After that, that's when it's forming helium into other things. And then those other things into other things, and those other things into other things. And you start getting these shells, kind of like the layers of an onion around the core of all the different materials. And that goes on until eventually the high mass star is going to explode in a violent supernova when it tries to fuse what element? The thing it tries to fuse that kills it is iron. So here I showed you a picture of the steel stacks. So, I mean, this crosses my mind every once in a while. We live in Bethlehem. Well, we don't all live in Bethlehem. I live in Bethlehem. You guys go to school in Bethlehem. And I'm sure you're aware Bethlehem used to have a steel industry. Well, steel is iron mixed with a few other things to make it stronger than iron. So, yeah, all of this stuff happened in a high mass star millions of years ago, billions of years ago. That high mass star died and exploded when it tries to fuse the iron, and then it shot all of that iron out into space. And that iron became part of a gas cloud, and that gas cloud eventually became a protostar and a planetary disk, and gravity brought all the stuff together, and the stuff in the middle of that giant disk became the sun, and the little clumps on the outer parts of the disk became the planets, one of them being Earth, which had iron in it from the death of this star. And then 4.5 billion years later, for a century and a half or so, there was a whole industry in Bethlehem where we would take that iron and do some stuff and turn it into steel. And we don't do that anymore for various economic reasons. So now we have concerts and things there. So that's it for this part. I hope you found it interesting. And I hope it sounded good. I would hate to think that I wasted my money on this microphone.